Hey guys, Mr. McKinney here, just doing a review of AP's Unit 6. This is a big unit. To put it in context, this is the unit that is over integration primarily. Um, Unit 6 is on integration. Unit 7 is on differential equations. Unit 8 would also be on integrals. It would be on applications. But Unit 8 is not on the AP exam this year. Unit 1 was on limits and continuity, and Units 2, 3, 4, and 5 were all on derivatives. So essentially we've got 1 unit on limits and continuity, 4 units on derivatives, and we really just have 2 units this year on integrals, and this unit on differential equations is not going to have nearly as many topics. So Unit 6 is a very big unit. Integrals, or antiderivatives, are broken up into 2 parts. You've got definite integrals, which is basically the area underneath the curve, and unders in quotes because it's between the curve and the x-axis. You have limits, a and b, for a definite integral. Indefinite integrals don't have limits. They're basically just the antiderivative, so what would undo the derivative? You'll have particular solutions and general solutions. General solutions would have a plus c, and if you actually find that c value, it's a particular solution. Particular solutions we'll get into a lot more in Unit 7 with differential equations. The way that definite integrals are introduced in calculus is with sigma or summation notation. And basically the idea is that if you want to find the area underneath a curve, which is what a definite integral is representing, you can approximate it with a bunch of rectangles. And sigma notation is saying, well, the number of rectangles is going to approach infinity. So we can make them infinitely skinny, add them all up, and that'll tell us exactly the area. If we could make all of these rectangles infinitely skinny and just add up all their heights, then we would get the area underneath the curve. The main thing for sigma notation is being able to find delta x and then using delta x to find x sub I, and then just plug that into your equation. The way you'd see it on an AP exam would either give you a problem like this and ask you to write it in sigma notation, or do the opposite of that. If you're trying to write it in sigma notation, the first thing you're going to want to look for is delta x. You can usually just get a point as long as you figure out what delta x is. So a is the number at the bottom, the lower limit. B is the number at the top, the upper limit. So in this problem, delta x would be 7 minus 5 over n. Then you're going to take that, plug it in for delta x here. K is going to stay k. A you can get from the lower limit of the integral. Once you have an expression for x sub I, you're going to plug that whole thing in for x. So wherever you see x, replace it with the expression that you get here. So I've got it all worked out on this next slide. Email me if you have questions. Another way that you might try to find the area underneath a curve with an approximation would be Riemann sums. So the next 6 slides or so just go through a variety of different Riemann sums. A left Riemann sum, you'd use a point on the left side to make a rectangle. Right Riemann sums would be on the right. Midpoint, you figure out what x value is halfway in between the rectangle and use that y value. You're not averaging the endpoints. If you were averaging the endpoints, that would be the trapezoid method, which is what we have next. You do need to know the formula for the trapezoid, 1/2 times base 1 plus base 2 times the height, because you won't always have equal intervals. If you just have equal intervals, then you can add these 2 approximations, the left and right, and divide by 2. But that's only if your intervals are all equal, so you wouldn't necessarily want to do that on the AP exam. All right. As I was saying, the interval is not always going to be equal. So for example, if I want to do the trapezoidal sum with 3 subintervals to estimate the number of people waiting in line during the first 4 hours. So we're not caring about the whole table. the first 4 hours. And we've got a graph that's got T, the number of hours, and then L, which is the number of people. Now, if we think about whatever the area underneath here is, the units would be people times hours. So if we want the average number of people, we'd have to take the number of people times hours and divide by the total number of hours. So I've got it all worked out here. So you can see for the trapezoidal sum, you're basically just figuring out how far apart are the x values. So these are 1 apart, these are 2 apart, these are 1 apart. So that 1 is here, that 2 is here, and then 1 again. So figure out how far apart the bases are, and then just add them together. So add those two together, then add those two together, and so on. If you are estimating with Riemann sums, you'll often be told if the original function is increasing or decreasing, or potentially if it's concave up or concave down. This table is a little bit modified from the one you saw in your notes this year, so take a look at this. If the function is increasing or decreasing, a left or right sum will be an over or under estimate. So if you have a left sum or a right sum, all you care about is whether the function is increasing or decreasing. It doesn't matter whether it's concave up or concave down. And to figure out if a function is increasing or decreasing, you're looking at the first derivative. So for left sums and right sums, you'd be worried about the first derivative. For a trapezoidal sum, you're worried about concave up or concave down, which is going to come from the second derivative. So if you're asked if it's an over or under estimate for a left or right sum, think about the first derivative. Think about these pictures. If you're asked for a trapezoid, then look at the second derivative and be thinking about concavity. Definite integrals have a few properties that you need to know in order to be able to manipulate them, especially if you don't know what the functions actually are. So the first one is the opposite property, which basically says if you want to switch the limits, just put a negative out front. Zero property says that the area between the same number is 0. So if the upper and lower limit are the same, the area underneath it is always 0. And then the additivity property basically says you can break up an integral into two separate integrals. So the integral from a to c can be broken up as the integral from a to b plus the integral from b to c. And it doesn't matter whether b is in between a and c or not. Here's a bunch of practice problems. I'm not going to work through each of them. I've got the answers on this next slide. So take a second and make sure you understand where they come from. The most common misconception is this plus 3. So you either need to think about this as the integral from -1 to 4 of f of x dx plus the integral from -1 to 4 of 3 dx. And then you can find this value using these integrals. To find this value, you should either think about the graph of the line y equals 3, and then what area would be underneath it. Or think about the integral. So the integral of 3 would be 3x, and evaluate it from -1 to 4. And we'll talk about that later on in this slideshow. Going back to our chart that shows the difference between definite and indefinite integrals. So far, those have all just been ways to measure the area underneath the curve. So let's switch gears and talk about indefinite integrals. Indefinite integrals, or antiderivatives, are just defined as the opposite of a derivative. So an antiderivative will undo whatever the derivative did. So the integral of lowercase f is capital F of x plus c. Integral of f prime is f, and the integral of f double prime is f prime. And you could go down as far as you wanted by taking the derivative. Remember that if you're doing an indefinite integral, you need that plus c at the end. You'll lose a bunch of points right off the bat if you don't put that plus c. If it gives you a piece of information about the original function, you'll be able to find c. So a lot of times it'll give you a point that you can use to find c. When you're doing indefinite integrals, there's a bunch of formulas you're going to have to memorize or have a cheat sheet for. So the integral of a constant, the integral of 5, would be 5x plus c. If you have a constant, you can pull it out in front of the integral, and a lot of times you'll need to do that when you're doing u substitution. This is the most important formula to be able to use, which basically just says if you start with an exponential, sorry, not an exponential, a power, then add 1 to the exponent, divide by the new exponent. So it's just the inverse rule of the derivative. You're allowed to add and subtract integrals. So just like derivatives, you can break them up and add or subtract them. There's no such thing as the product rule or the quotient rule for integrals. So if it's f times g, you can't break it up using some sort of power rule or anything like that. Here's a few, the first transcendental integral formulas we learned. So integral of sine is negative cosine, integral of cosine is sine. As long as you know the derivative rules, you're fine. The derivative of sine is cosine, the derivative of negative cosine. Well, the derivative of cosine is negative sine, so the negative derivative of cosine would be positive sine. Integral of e to the x is e to the x plus c, just like the derivative of e to the x is e to the x. And the integral of 1 over x dx, or sometimes you'll see it as dx over x, would be ln of the absolute value of x plus c. Remember that you need the absolute value here because the domain of a log needs to be a positive number. You can't put negative numbers in the domain of a log. Here's a few more integral formulas. Just memorize them or have a cheat sheet. And these ones you're definitely going to want to have written down somewhere since you're allowed to have a cheat sheet. So these are the formulas that will give you inverse trig as you take the integral. You're going to have to use u substitution on almost all of these to make them match one of these formulas. So those are the formulas you have to memorize. We've got 4 slides worth of formulas. If your problem does not perfectly match one of those formulas, then you have to use u substitution. Here's an example of how we'd use u substitution. So x times 8 minus x squared to the 6th power. We're taking the integral of that dx, so with respect to x. Like I said, there's no such thing as the product rule. So in this problem, I'm going to say, okay, u, some new function, is going to be equal to 8 minus x squared. So if I took the derivative of u, it would be negative 2x, and then I need to remember a dx. So I have a dx, I have an x, but I need a negative 2. So I'm going to put a factor of negative 2 on the inside, which means I need a factor of negative 1 on the outside. So now I can rewrite this as u to the 6th. This whole thing was u. So the integral of u to the 6th, I had a negative 1/2 out front, and then this negative 2x dx turns into du. This didn't match one of my formulas. This does. So now I can take the integral. So keep the negative 1/2 out front. Since this is a power, I'm going to add 1 to the exponent, divide by the new exponent, and then remember your constant, so plus c. And then if you're using u substitution with an indefinite integral, you have to plug u back in at the end. So negative 1/2 times times 1/7 would be negative 1/14. Instead of u to the 7th, I'm going to have 8 minus x squared to the 7th plus c. I think that's going to be about it for this first video. Hope it helped.